Okay. We're gonna start off with, like I said, stacks and queues. And since nobody said they wanted the explanation of like stacks and queues, then I'm just gonna hop right into the question. But I do want to explain just one part real quick. Um, just a little overview. So let's start us off with stacks. So when it comes to stack, there's one thing you always have to remember. It's what type of data structure it is. So LIFO, that means last in, first out. So imagine you have a box or a stack of plates, and you're not going to be adding stuff to the stack at the bottom of the stack, right? You're always going to be adding to the top of the stack of plates, to the top, to the top, to the top, and so on. So that's one distinction to make with stacks. You're always going to be adding to the top, and let's say you wanted to remove, so we have these plates. So you want to remove this plate right here. You're going to remove it, and then now your new top of the stack is going to be this one right here. So that's going to be the topmost plate. So let's say you're cleaning dishes, you pop this one off, right, and you clean it off and everything. Then now the next one you're going to deal with is this one down here. So that's one distinction. And like I said, there's two implementations. There's linked lists. So just for a quick overview, if we keep the same model of like plates, for example, let's say we have a plate in our stack of plates. If we wanted to add something on it, assuming this is linked list, right? We're going to be adding to the head of the linked list. So let's say this was the head right here, and we wanted to add a new plate onto our stack. We would make a new node, and for the purpose of this, we can say this is going to be 3, this is going to be 4, this is going to be 5. We would want to reroute the next pointer of the new node to point to our old head, and then reassign the old head to be our new head, or the new node to be our new head. So what that would look like is now we would have something like this right here, and this would be our head. So now we just added onto the stack of plates. If you want to remove, you would move the head pointer forward and then remove this node from memory, so you just free that one. So I just wanted to get through that real quick when it comes to linked list based stack. When we're dealing with arrays though, there's two types. So there's 0 based, and then we have -1 based. And this is just referring to the top index. Let's do top index. So if we're 0 based, let's say we have a stack of 4 items. If we start at 0, so we would be pointing here. If we want to add something in, 0 is the first location that you can add something in. So let's say we wanted to add 1. Then we would move our top index from pointing to 1. Since we added something, we would move it to the next available slot. So that's for 0 base. You would add where you are currently, then you would increment. And then once you increment, when you go to add something else onto the stack, that position is going to be where you're going to add it into. So if we were going to add something in, we would index into where the top index is right now. So this is index 1. And then we would add the next element. Do the same thing. Let's say we wanted to add 4. We would do the same thing again. So we want to add 7. And then now our top index would point out of bounds, right? So we know that we can index into 0, 1, 2, and 3. But now that we're at 4, this means that we're at full capacity. And assuming we're not going to have to like resize where we have the stack based in memory, like it's just a static like 50 or 4 element array for your stack, then whenever you hit this point, you're not going to be able to add anything on it. This is going to denote when you're at full capacity. Now, where it comes to an -1 base stack, then it's going to be a little different. So if we're at -1, in this case, when we were in the 0 base stack, we would add to where the index is, and then we would increment. But in this case, if we index into an array at, like, let's say we do array -1. This is not something you can do in C. If not, you're probably going to hit a segfall or something like that. So you would want to increment. We're currently pointing right here. You want to increment, and then you would add your element. Same thing. Let's say you want to add another element. You would increment, and then you add the element. Increment, then you add the element. Then here you would increment and then add the element. And once we get here is where you're going to realize, like, you're not going to be able to put anything else after this point, because then if you go past this point right here, you would increment and then you would want to place something here. But this is the same case that you had here, just that you're going to be out of bounds as well. So when it comes to a -1 base stack, when you're at full capacity is going to be when your pointer points to n-1. So let's say in this case, n is 4, because we have an array of size 4. That's going to be your capacity. Whenever your index on a -1 base array or stack array is pointing to n-1, so index 3, then in that case, we're at full capacity. So capacity equals n-1, that's full. And in this case, say n is 4, capacity, sorry, let me rewrite this, not capacity. I mean the top index. So that's gonna be your top index. When your top index in the 0 base is equal to capacity, that's when you're full. And in the other case, when your top index is equal to capacity -1, that's still n. So this is going to be denoting when you're full. So I just wanted to get that out the way real quick, so we know how this is going to work. When you're -1 base, you're going to increment, then you add. When you're 0 base, you're going to add, then you increment. And the code is very similar. It's going to change literally one line and just flip them around, and that'll be it. Okay, so now let me see if anyone has a question real quick. No one. Okay, cool. So now we're just going to hop straight into the questions now that we have that out the way. So let's start with this one right here. Well, let's go with this one. This is a stack question. Okay, just give me a sec. Okay, so this question is saying that suppose we have a stack implemented with an array. I'll let you guys read it so I don't make any noise, Okay, so it says that you get a pointer to the current stack and an integer representing the amount to increase the capacity by. You may assume it's not null and points to a valid struct stack. You may assume the capacity stores the current size of the array. Pointer array, it's pointing. Top represents a number, the current in the stack. Okay, cool. So we're given a pointer and we have to increase it by a certain amount. So if we can assume that it's not null, that means we don't have to have any if check based on that. So it seems like the next thing we're going to have to do, first let's notice that we have an array pointer. So it's not static. So that's how we're going to resize it. If it were something like array 50, then in that case we wouldn't be able to resize it. But since it's a pointer, you can dynamically allocate it and then you can resize it from there. So the way we're going to do this is we're going to take the capacity. So we know that the current capacity, it's going to be the size of the array. So let's say we have the size of the array of 4. So capacity would equal 4 here. And let's say we have increase to be equal to 3. Then if we have, for example, 3, 4, 2, 1 in this array, we're going to want to transfer it over and expand the size of the array. 1, 2, 3, 4, 5, 6, and 7. So 0, yeah, it's 7. So we're going to do 4 plus 7. That's going to be 3. And we're going to have to transfer everything over. So we have 3, 4, 2, 1. We're just going to transfer everything over, and we also want to copy over what the top is going to be as well, because it's saying that we just want to grow the stack. We don't want to add any element onto it. So top is going to stay the same. The only thing that are changing is the pointer to the array, which is just going to increase, and then the capacity of the stack, because it's going to be tied to, how many elements we can access and so on. So I'm just going to erase this, and then we can go ahead with the question. So we don't have to do a check, but store a pointer for the new array. So this is going to be new array is equal to, and we're going to malloc it based on the size of the integer. So this is going to malloc the amount of space that we need for the new capacity. This is going to be times, we have some information we're going to use from stack. We're going to do stack capacity. So that's going to give us the current size, and then we're going to want to increment that by increase. We're going to make it bigger by increase. So as of right now, we've malloc an array of the old capacity plus the size we wanted to increase by. So now we have the full capacity that we're going to want in our new stack. So now that we've done that, we're going to want to copy all the elements over, because right now what we just have this array of the new size. So it's going to be capacity plus increase. And now we're going to copy every element over that was previously in there. So we're going to iterate through the array. The way we're going to iterate through that is we're going to take the stack capacity. Notice that I didn't increase the capacity itself. I just added onto it because I knew I was going to use it later on. Okay, let me just make sure something with this question. Okay. So now we're going to take new array of the current element x. I called it something else. New array x equals, now we're going to do s of, and the array was called array of x. So now right here, we've copied everything over from the old array into the new array. And now we can free the old array. Because now we're done with it. We don't need it anymore. We've gotten all the information from it. So we can free it. We can reassign what the pointer was. So we're gonna have array equals new array. The top is gonna stay the same, but what is gonna change is the capacity. So now we're gonna do as capacity plus equals increase. And that should be everything. So we've malloc the new array to the size that we wanted. We did a for loop, we iterated through the old array on the stack, copied everything over up until the index that we previously were able to. So if we could go up until index 4 or index 3 and wanted to add on 3 elements, we only have to copy over this section right here. Everything else after this, there's nothing there. So that's why I only did it up until the capacity. And yeah, free the old array. We assign the new array pointer. Then now we're going to increase the capacity so that then the next time we use it, we know the actual capacity that's actually at, the updated one. And that's it for this question. So you can assume it's not null. Yep. Okay, that's it. So does anyone have any questions on that? Would you use a temp pointer, then allocate space, and then transfer over? Yeah, exactly. So you want to use temporary pointer, allocate the space, transfer it over. Then you'd have to free it. Once you free it, you increase the capacity, you reassign the pointer, and then you're done. All right, everyone. So I'm gonna go ahead and start. So hey, it's me, Zain, again. Last time, if anyone of you guys were here last time, there was some issues like with my iPad, with Zoom, and I wasn't able to, complete the session. It only ran for about 30 minutes, but now everything should be good. I tested some stuff out, so I don't think it'll be happening again. But we're gonna continue back off where we left, and that was with stacks and queues. All right, so we're gonna go ahead and start off. So I spoke with some people and they asked me for some recommendations of, how I should format this. So I'm gonna have a text editor here, so I can code up anything that needs to be coded up versus writing it because it takes longer and it gets a little messy. My handwriting might not be the best. So for the questions that that are more visual involved, I'm gonna draw it out. For questions that are more coding related, I'm just gonna write it out in the text editor like this. So yeah, we can start off with the first stack question. I've selected out some questions from the foundation exams because some people also wanted to do that specifically. So we're gonna start off with stacks. There's gonna be a couple Q questions in here as well. So yeah, we're just gonna go through them, not in no particular order. Okay, so I'm gonna have this question up and you guys can take a second to read it. I'll start writing everything out. Okay, so that should be enough to read it. Let me see if anyone has any questions on the question itself. No, okay. So pretty much they want you to evaluate a postfix expression. You have positive numbers, and those are going to be like what you're going to be adding and subtracting. They're going to give you some integers, -1 and -2, and that's going to be denoting like sort of operations. So addition would be -1, -2 would be subtraction. So we'd have to have some checks for that. One thing to note though, that seems to trip up a lot of people on the, on these type of questions, it's pretty subtle, but if you do the questions enough, you'll get to see it or you'll notice it. He gives a stack that's statically initialized. So if you were to access something in it, it would be, like s dot top, for example, or s dot next. But all of these functions, they take in a pointer. So if you don't do something, for example, like the ampersand s in every single one of the functions, like push ampersand s and then some sort of integer, you have to put in the pointer to it. If you do just simply s itself or s like this, just s itself, they're going to take points off. So that's one thing to note for this function. So if we think about how a postfix expression works, let's test this on two numbers. Let's say we get 4, 5, and plus. In the case of this example, -1 is addition. So I'm going to have it like this. So this is going to be our expression. And the length of this is 3 because we have 3 like operator and operands together. So 4 and 5 are the operands. -1 is plus. So that's an operator. So if we have this postfix expression, we should end up with 9 at the end because we would do 4. We see a -1 and then we take the previous 2 elements and add them together, and that'll leave us with 9. So that's pretty much the idea of how this is going to work. Let's say we had something else, let's say a 5 and then a -2. So if we're reading this left to right, we would have 2 items. So we would have 4 and 5, and we would have -1. And remember, postfix, it requires 2 operands to do an expression or to do an operation. So notice how it says here that you're given a valid postfix expression. So that means that there's never going to be a case where, you have an addition that you're doing, but there's only one element or something invalid like that. You always need 2 elements and it's always going to be valid. So that's something you don't have to consider. So in this case, you would come to the -1, take the 2 previous elements, put on a 9, but you would pop off the previous 2. So 4 and 5 are gone. Then you would run into this 5, don't do anything. You're going to run into this 2 or -2, and that denotes subtraction. So it's going to pop off the 2 previous elements, and you're going to have 9 minus 5, and that's going to be 4. So your final answer in this expression would end up being 4. 4 plus 5, 9. 9 minus 5 is 4. So that's the whole idea of how this is going to work. So first things first, we're going to want to run through the expression. Notice how they give us a integer pointer, XPR, EXPR, and then length. So this is going to be an array we're going to run through. I'm going to use X to iterate through it. Okay, so since we know that it's a valid expression, we don't have to do any special if checks. Like, for example, if X is less than 2, like if X is less than 2, so if we're at 4 or 5 in the expression above, you're not going to do anything, or you're not going to, try to do any checks for anything special. You're just going to assume that it works. So we're just going to be checking here. If EXPR, so if the current thing that we're on in the expression, we probably want to check if it's an operator or if it's an operand. We're more interested in checking if it's an operator, meaning plus or minus, or addition or subtraction. And that's going to be noted if the value is less than 0, meaning it's negative. So we could do something like if expression of X is less than 0. Another way you could do it is just if it's -1. Have another case, else if expression X equals -2. So I'll just go with this. And then I'll have an else. So this is going to be the add case. This is going to be the subtract case. There's going to be the push case. This is because we're going to want to have at all times in our stack for postfix, we're going to want to have the numbers themselves to validate the expression. So the cases we're going to run into first is just going to be the else, which is going to be, we're just going to have elements we're going to be adding on. So else, I'm going to take this stack S and I'm going to push. Remember, we have these three functions: init, push, and pop. So we're going to want to push the current item on. So in this case, we would start off at 4. So we're going to want to push 4 into our stack. So I'll have this here. It's going to be our stack. And now I'm going to do %s. Remember the ampersand, since we got to do pointers. And we're going to want to push whatever the current element is onto the stack. So this is going to go 4. Then we're going to hit 5. Now that we passed 5, we're going to add it onto the stack. And then now we're going to hit -1. So since it's negative, we're going to be doing an operation. And actually, I'm going to rewrite this so I don't have to rewrite some code. I'm just going to do if less than 0, because in both cases, I'm going to be popping off. So I don't want to, repeat the popping for the -1 case and -2. I can just do it all in here. So if it's less than 0, we know it's an operation. So we're going to want to, so we don't have access to a peak or anything like that. And we actually don't need it. We're just going to take whatever it is. So if expression x is equals -1, else if it's not -1, it has to be -2. Just write this here. Add. And we're going to have to get the elements we're going to add or subtract with. So the way we can do that is by taking things off of the stack. We just push them on if they're not operators. So now we're going to pop them off so we can get access to them, since we don't have, peak. And either way, if you use peak, you can only peek to the top, not the element under that as well. So we're going to do int pop. Let's call it val1. That's going to be pop %s. And then val2. Actually, I'll write it a little differently. Int val2 equals pop %s. So now we have the two elements popped off. So if we're back at the stack up here, now we have an empty stack. And we're currently on this element right here. We're currently at -1. So what we're going to do is we're going to push onto the stack val1 plus val2. So since we're doing since we're doing addition, it doesn't matter which way you put it on. So 2 plus 1, 1 plus 2, it doesn't matter. But when it comes to subtraction, you're going to want to order it the second element you popped off. So second plus first, or minus first. Because of course, if we do that in a different order, like first minus second, we're not going to get the same answer. But when it comes to addition, we would. So we're going to want to be a little more careful in this case. Val2 minus val1. And I'll just rewrite this one, so it doesn't matter. Just keep it uniform. And let's just run through this right here. So like I said, we had 4 and 5. Then we pop these two off. 4 plus 5, it's going to give us 9. Then we're going to move on to the next element. It's not negative, so we're going to add it onto the stack. Then we're going to go to the next element. It's negative. It's subtraction. Pop these two off. 9 minus 5, 4. So at the end of the expression, notice that you're going to be left with one value. And when it comes to like a lot of the postfix questions that you come up on the foundation exam, at the final stack, depending on the question, it'll end with one single value. So after a valid postfix expression, after you evaluate it, it's always going to have one element in the stack. So at this point, after this for loop, we've processed everything properly. And now the only thing that's left to do is see what it returns. It just evaluates, yeah. So we just return pop ampersand s. So since we would be left with one element, we're just gonna pop it off and return that. So we would return 4. And that would be the solution for this question. So just to run through it again, this is what they gave us up here. Oh, they actually gave me an I, but I didn't use it. Okay, so iterate through it, go through the expression. If it's negative, then that's where you're gonna pop off the 2 elements. Oh, I actually have a typo here, plus. Okay, so you're gonna pop off the 2 items. If it's negative, it doesn't matter which way you add them, but you're just gonna push on the addition of the 2 elements. Meanwhile, if you're doing subtraction, you're gonna want to do the second item you pop minus the first item you pop. And it's good to just keep that, even if it's addition, it doesn't matter, the same format. So, you don't forget. Else, if it's an operand, you're just gonna push it onto the stack so then it can be evaluated later down the, the expression array that we have. And that's pretty much it for this question. So does anyone have any questions? No? Okay, cool. So we're gonna go on to the next question. So that was one right there. So this next question, honestly, I remember laughing when I first saw this, but it's a good question regardless, I guess. So consider modeling cars lining up at a traffic light in a simulation. Which would be better to utilize, a stack or a queue to store the cars? So I guess the best way you can think of it, let's say this is I'm just drawing here. Oh, interesting. Okay, there we go. So let's say you're at a traffic light, right? So this is your light right here, or whatever they look like. This is a traffic light, and this is your car right here. If you're at the front of the line, do you want this guy to go past you first, or since you're closest to the stoplight, you want to go first? So another way, that's kind of like a bad explanation, but if you're at a line for Chipotle, let's say this is the counter right here, this is the cashier, and this is you. You got here first, and then there's a couple other people ordering. Do you want this guy to leave before you? No, you were first in line. Same thing when you're in traffic, you're the first in front of the light. So it would be best if you left, first because you got there first. So that's where the principle of a queue comes in, knowing like how a stack works versus queue. So queue, FIFO, first in, first out. You were the first in line, you were the first one to leave. Meanwhile, stack, last in, first out. So in the same case, if this guy was last, he would leave first, but that's not fair. You were the first at the line, So that's how that would work. You would want to use a queue to store the cars because it just makes more sense, For the first person in line should be the first one leaving. So that's one question right there. Now we have some more queue questions. And this one I'm gonna draw out. Okay, so I'll just have it here so you guys can read it out real quick. Okay, so they just give us a sequence of lines of code of how things are unqueued and dequeued and so on. And they want you to replicate the state of the queue after every single line of code. So really this struct here, it's kind of useless. There's no point of having it. As long as you know the properties of how a queue would work in the array, you could probably figure it out without having a struct, but they just gave it to us. And they just said some minor stuff. It's initialized to 0 and everything. There's nothing in the queue before you add anything. And that makes sense. So indicate the front by making bold the element at the front of the queue. Okay, so I'm going to use red for the front of the queue. I'm going to use blue for every other element. So when it comes to queue that are implemented with an array, the whole formula when you're going to onqueue would be, so you have queue, let's say this is array, have queue front plus queue, I'll call this num_l, so I don't have to write it all out. Mod queue cap, so that's capacity. And you would set this equal to item. So this is a formula for when you want to onqueue into an array-based queue. And this is assuming you're not at full capacity for your queue and everything. So let's assume we're not full and we don't have to do any if checks and so on. So this is how it would work out. So we can use this formula if you want, if you're not familiar with it, to simulate like how this is going to work out. So the front is always going to start at 0 because there's no one in line. So it can't be at 1, 2, 3. It could be, I guess, but for the purpose of this, let's just assume it starts at 1 or at 0, sorry. So it says onqueue 50. So we're going to start by onqueuing 50 right here. So 50, then it says onqueue 34. So queue front start at 0. So we're going to do queue front plus number of elements. So this would have been 0 plus 0 mod capacity 5. So we have 0 mod 5, that's still 0. So that would be where we're going to be at for the first insertion, first addition. Then we're going to do the same thing, but queue front, it would have been incremented. So we would have moved it up by 1. And by the way, the formula for that part would have been queue front equals queue front plus 1 mod queue capacity. And the whole thing with mod is you want it to wrap around in case there might be space at the left side of the array, left side of the front, like to the left of the front in the index based on its index, but you're going to want to wrap around in case you exceed past the capacity of the array, so you don't segfault. So we would have incremented it, and now our front, this is for a DQ right here. This is DQ. This is when you update on a DQ. So that's going to be relevant for when we get to 4. But we're going to onqueue. Our front would have still stayed at 0, but now we have an element. So 0 plus 1 mod 5. 1 mod 5 is still 5. It's still 1, sorry. Then we're going to onqueue 91. 0 plus 2 mod 5 is 2. So that's going to give us index 2. So that's right. Now we're going to get to step 4. X equals dq of q. So here we're going to introduce a variable x equals, and we're going to want a dq. So that means we're going to be moving this forward, and I meant to write this here. So let's just, this is 50, 34, 91, 34, 91, 50. Okay, sorry about that. In case you guys were confused. So now we're going to be at 4, and we're going to want to use this formula right here to do the update on the DQ for the Q front. So we're going to set X equal to what's at the front of the Q, and that would be 50. And then we're going to use this formula. So Q front is going to be equal to, so we have 0 plus 1 mod the capacity. So our new front is going to be at index 1. So that makes 34 our front right now. 91 is not the front. So our number of elements went down, and it went down by 1 since we just DQ'd an element. So now the number of elements we have is just 2. So we set X is going to be equal to 50. So we can just remember that right there. Statement 5 on Q23. And the on Q part is kind of the easiest. So start off, we have 34. I'm going to have 91 on Q23 at the end. Then we have variable Y we're going to introduce. We're also going to write this one down. And it's going to be 34. So our front would increment to, it was at 1 plus 1, mod 5, it gives us 2. So now our front is at 2. So 50, X is 50, 34, Y is 34. So now the state of our Q is 91, and we have 23. So right now we are right here. So we're on Q, Y, and Y is 34. So we're going to have 91, 23, and this is the wraparound case. It's going to be 34. So the way that would have worked is we would have had Q front. So Q front, just give me a sec. Oh, the wraparound key is actually the next one. Apologize. Okay, so after statement 7 on Q15, this is a wraparound case. So I have 91. I have 23, 34. Then statement 8, that's where we're on queuing. So we would have the wraparound here. It's going to do the math. So if front is at 2, we have 3 elements, 2 plus 3, mod 5 is going to be 5 mod 5, and 5 goes into 5 evenly. So that would give us index 0. So now this would be what you could call the tail of the queue. So that's a wraparound case right there. So we just got done with expression 8, statement 8. Now we're going to do expression 9 on QX. Remember, X was 50. So it's still going to follow the same logic. So 91. Then we're going to have 23, 34, 15. And now we're going to have 50 here. And X is going to be equal to DQ of Q. So we're just updating X, but at this point, since it's the last expression, we don't really care what it is, but we'll just set it to 91 just to follow the same pattern. So we're going to move our front by 1. So 23 becomes our front, 34, 15, 50, and this is the final state. So let's just go through one more time. On Q50, it's our front. Then we on Q34, 91. We're going to remove 50, and then our front is now going to be 34. Going to add on 23. Remove 34. That's expression 6. Then we're going to add on y, which was 34 right here. On cue another element. This is the wraparound case. Then expression 9, we're going to on cue 50, which that was x was 50. So now we have a full cue, and then we're going to pop off the front. Our front is going to move forward, and this is where our front ends up at. And this is the final state of the cue right here. So does anyone have any questions with that? So let me see. Would it be a cue since you want first in, first out system? If 5 mod 5, how come 15 is in the first spot of the array? Oh, did I say it equals 5? I don't think I did. I think what I had written out was 5 mod 5 equals 0 because it goes in evenly. So pretty much the rules for mod. So let's say we have, there's going to be a little bit like discrete. We have A and B. We have integers A and B, right? If A, and let's assume they're positive. So let's say positive A and B. If A so in this case, if A is less than B, then the answer is just going to give you A. So if we do 3 mod 5, 2 mod 3, we're going to get 3. So we're just going to get A itself. We're going to get 2 itself. Meanwhile, if you have a case like, let's say we add on a little bit to this. So we have greater than or equal to. This case, it'll be A or 0. So it would be the same case. Since we're doing less than or equal to, we could have a case where it's smaller. So 2 mod 3, that'll give you 2. But if you do, for example, 3 mod 3, that'll give you 0. Now, in another case, let's say A is bigger. So let's say we have 5 mod 3. That'll be how many times 3 goes into 5 plus the remainder. So 3 goes into it once plus 2, and that'll give you 5. So really the way to look at it would be Q times M plus R. So you would have 3 times 1 plus 2, this will equal 5. And what this expression here would give you, it would just be whatever the remainder is. So yeah, that's how that would work. So yeah, 15, if it was 15 mod 5, it would just give you 0 itself. Oh no, you're good. Okay, so let's go to the next question. Okay, so I'll just have it here so you guys can read it real quick. I'll type it up. Okay, so should have been enough time. So you're dequeuing, and this isn't what we're normally used to for a queue. This is a doubly linked list. Normally, you do it on singly linked lists, but yeah, this time it's a doubly linked. So just a refresher, for doubly linked, you have something that looks like this. So let's say this is your head. This would point to null. You have a link from here, and you have a link back to here. And right here, you have a link to null. So pretty much on both sides, you have a null. The previous of your head and then the next of the tail are both going to be null. So that's one thing to keep in mind. So we want to write a dequeue function, and if it's null or empty, return 0. So when it comes to linked list queue, the way that they're implemented normally is that you're going to be removing from the head. So think of when it comes to arrays, you would have a front pointer. Let's say this is your front right now. In this case, the front of the linked list is always going to be, or the head of the linked list is going to be your front if you're thinking about it like an array. But we're dealing with linked lists. So the way we would, dequeue something off, let's say we have something like this. This would be our old head. And then let me just write in blue the new head. So we have these links. So the idea is that, let's say this is value 3, this is 4. We would store 3. So we have 3 stored right here. Then we would store a reference to the new head. So let's call this new head. New head. We would free this node out. Let me just isolate it. Okay, there we go. So we free this out. And then now, instead of being our new head, we're going to make our new head, which was just the next of the old head. We're going to make that our head itself. So it goes from being the next of the old head, and it just becomes our head. But if you notice, there's still some things that we got to deal with. So since every single one has every single node has a previous and a next, you're gonna have to handle this pointer right here, because it'll still point to an address in memory, but we just want it to point to null. So that's one thing. So instead of having this link back to whatever this was, we're just gonna point it to null. It's gonna point to null. Meanwhile, everything else from here up until the end of the list is going to stay as it was. So yeah, there's just some small cases. Let me see if anyone has a question real quick. No. Okay. So first things first, if this queue is null, or, and I'm just doing this in one line to make it quicker, or it's empty. And we actually have 2 ways to check if it's empty. We can check, or actually 3 ways. If size is 0 on the queue, or if the head is null, or if the tail is null. And the reason that head and tail both could give us the same, like size is self-explanatory. You have nothing, it's just going to be 0. The head and tail at the start, let's say you have nothing in your linked list. Your head and tail are actually going to be at the same spot. But then the moment, they're both going to be pointing to null. And the moment you add something else, let's say you have just one node, this is still going to be your head and tail. They're still going to be at the same spot. But the moment you start adding another element, and that's where your tail starts sliding down towards the right side. So you can really check 3 ways to see if it's empty based on the struct that they give you, but I'm just going to go by the size. So this handles the empty case. And now we just have to handle the case where we don't have an empty queue. So we have something to work with. So first things first, we're gonna wanna store a reference to the next head. So whatever the new front is gonna be. And our struct, this is what we're given next. Okay, cool. So we would do node star, call this the new head, and then we're gonna do this queue head next. So after this line, we know that it's not empty, so we have something to go off. And regardless if the next of the head is null, it's still gonna work out fine. But we're just gonna have to do a little bit of checks for that. But we're gonna store the new head. So like I said, we've now stored in this old example, we now have where 4 is at, we have a pointer to that. So we're gonna wanna free this queue head. So now that we freed it, we just took it out from memory. Now we're gonna wanna reassign. So remember the old step where I said you take the old head, free it, take the reference to the new head, and that's gonna be your new head, or that's gonna be your head. You're gonna say this queue head equals new head. So now we freed it and we advanced our pointer to the next element. And this is where we're gonna wanna do a check because there's two cases. So there's a case where for, so there's a case where if 4 is null or if it's non-null. So let's say we had just one element in the queue and then we wanted to dequeue it. So let's say this was 3. So now we have the value 3. Oh, and actually I forgot to take that. So let's do it real quick. So reval this queue head, and it's called data. Okay, so now we have the value. So we took the value 3. Okay, that's a really bad 3. 3. So now we have value 3. Then this is our new head. This is our old head. We're gonna take the value. We took the value. Then we're gonna move it forward, and then our new head becomes our head. In this case, our head is null, right? So we have null. And the thing with null, remember how I said if you move it forward, you're gonna have to reassign the previous pointer of the head that you have now. If it's null, you can't do that because if you do something like this, previous, you're gonna get segfault because null is nothing and you can't check if nothing has a previous. So you're just gonna wanna check real quick if this queue head does not equal null. So if it doesn't equal null, that means we're okay to go ahead and reassign the previous of our new head. So we're gonna have this queue head next, the previous is gonna be null. So you could have done it this way. Another way you could have done it as well was just to do it right here. So you could have done new head previous. Actually, you would also have to check if it's null in that case as well. So it's best to leave it like this. So if it's null, if it's not null, then we can access it and then reassign it to null since it's now going to be the front and there's nothing before the front. And the next thing we got to do, this queue size -1. So we just decrease its size. And from there, we just want to return the value that we have. So just to recap, we check if it's null or not, if it's empty. If it's neither of these cases, then we're going to keep on going. If it is, we just return 0. We're going to want to store the value at the head since we know it's not null. Get the new head. It could be null, but at this point, we don't care. We free the old head, we reassign the head to be the new head. Then we check if this new head, if it's non-null. If so, then we can reassign the previous to point to nothing. So we can pretty much set it up like what we have right here. And then from there, we just decrement the size and we just return the value that we had. And then now we just perform a proper DQ. The next pointer, we don't really have to touch because it would already be pointing to where it has to. So yeah, that's good. We're only concerned with the first element. And if there is more than one element, the pointer of the second element, which would then be our first. Okay, so let me see. Doubly linked list. If we're dealing with a node in the middle of the list, we wouldn't reroute the next and previous pointers rather than delete them. Well, if you're deleting in the middle of a linked list, you would have to reassign the pointers actually. And that one's a little bit more tricky. It's not really it makes sense. It's easy to, but it's like a little bit more hands-on, I guess you can say. So I'll just go through that example real quick. You wouldn't want to reroute it, but like you wouldn't want to reroute anything of the node that you had, but you want to store pointers to like what something used to point to and so on. So let's say we're doing that. Let me just draw it out right here. Let's say we have a case like that where okay, I'm just gonna draw X. That's null. So we have 3, 4, 5. 3, 4, 5. Okay. Oh, and also this one right here. So let's say we want to remove 4 right here. So we're gonna have our iterator. Let's call it C. So C is gonna start at 3. Then let's say you're looking for a 4. For whatever reason, you want to delete the 4. So what do you need? If you're gonna remove the 4, you're gonna have to link whatever's on this side of the array and whatever's on this side of the array, or up on the linked list. So the left side of the linked list from 4, you're gonna want to link to 3 or to 5, the node containing 5. So how could you get from 3 to 5? You would have to store, let me just highlight it here, let's do it in green. You would have to store what the next of the node that you're deleting was. And you also want to store the previous of the node that you're deleting. And the reason why that's relevant is by having this link right here, you can reroute the next of 3 instead of pointing to this old node, we can reroute it to point here. And the reason we want the previous of the current node, so the node we deleted 4, is so that then you can reroute this previous from 5 to point to 3. And let me just draw a little bit away from that because it's got a bit messy. Now we're going to end up with something like this: 3, 5. So this is going to be our new linked list. So we just deleted 4, and actually one thing, normally when you do deletion, you are on a singly linked list. So let's say we had the same case but on singly linked. So we have 3, 4, and 5. If you want to delete 4, there's different ways to do it, but the problem with deleting 4 is you would have to be here. So you would have to be, let's say this is your current. You would have to be here to delete 4. So then you can connect this half of the list to this half of the list, or that part of the list. Or you could be here but have a previous. So like, for example, The next iteration of this would be something like P and C. So P would be your previous and C would be your current. That way you don't have to be at the node you're gonna delete or before it. So I wouldn't have to be at 4 to delete 5. I could be at 5 and delete 5 because I had a link to 4. But generally, and the easiest way that people do it is if you're right here and you want to delete this one, you would have to be right before it to delete it. So you would reroute like this. But the thing is, with a doubly linked list, you have the advantage that you know who your previous and current is. So you could just stop, like in this case, we stopped at the node that we had to delete, and then we had all the information we need. So that would be like the difference between deleting on doubly linked versus singly linked list. So I hope that answers your question. Let me see. Oh, okay. All right, yeah, I'm gonna go to the next question. Okay, so you guys can read that. Okay, so that should be enough time. So you're pretty much reversing stuff on one stack and throwing it into another stack. So let's say we have a sequence of numbers. Let's make it simple. 1, 2, 3. You want to return a pointer to a newly created stack that reverses the order of the item. So you just want 3, 2, 1. And this is a linked list version of a stack, but it doesn't matter. You're using the functions to do all this stuff, so you don't have to, do all the dirty work of next and head and so on. So you're just using functions. So pretty much, let's say it doesn't matter the way I draw it. This is going to look a little bit like an array, but let's say you have a stack 1, 2, 3. The whole idea is you want to reverse its contents. So if you remember the property of a stack, it's last in, first out. So that means if we were to pop it, let's say we want to just pop everything off in this whole stack. We would, oh gosh, okay. We have 3, pop it off. And then now we have 2 elements. Pop it off, 2. And then now we're going to have 1. So if you notice, our stack previously was 1, 2, 3. So by popping everything off, you have everything in reverse order. And same way, let's say we had a stack 3, 2, 1. If we pop it off 1, pop it off 2, pop it off 3. So in terms of bottom up, we had 3, 2, 1, but then top to bottom, we had 1, 2, 3. So it's reversing whatever's in the stack. So if you think about it, if we take elements from one stack. So again, 3, 2, 1. And we have another stack. If we pop this element off and then we put it somewhere else, in this case, that somewhere else is another stack. So based on the property last in, first out, that means that first in would be the last out, if that makes sense. So I'm just flipping this meaning right here. Last in, first out. So the last in right here was 1, right? So the first one out would be 1. But if you take like the thing that I said, first in, last out, the first one into the stack is going to be the last one out. So pretty much we first started off adding 3, 2, and 1. This is the state of our stack right now. But then we're going to have 1, 2, 3. And that's going to be at the top of this stack right here. So that's pretty much what we're going to want to do. Take stuff from one stack, push it onto another. And now we went from 3, 2, 1 from bottom up to 1, 2, 3 bottom up. So that's pretty much all we're doing here. Let me see if anyone has a question. No, okay. So I'm gonna just go into the code. So we already have it malloc because he gave it to us that way. So we're just gonna wanna set up some stuff. Notice he malloced it for us. There's no initialize function. So they're expecting you to do that yourself. So what do we have to initialize? Just look at the stack yourself. We have to set new s. So size, there's nothing in there. So 0. Since there's nothing in there, we're not pointing to anything. So it's just null. So we just initialize the stack right there. So that part is done. Now we have a valid stack to work with. Now we're given one stack. So it's s. We're given s. And we have a function here, is empty. It returns 1 if it is empty, 0 if it's not empty. So you can check if it's not empty. So meaning if it returns 0, that means that you're not empty. And pretty much what I'm doing here, let's say we have a stack 1, 2, 3, and then we hit this while loop. It's going to say, okay, it's not empty, so it's going to return 0. And then what you're going to do, you're going to negate the 0. So 0 is equivalent to false, and then we're going to negate it. So if the opposite of false would be true. So pretty much while we're still not empty, we're going to keep on removing elements. So we can remove from one stack, and I'm going to show you when we're going to do that. But the whole idea, we're pushing onto a different stack. But what exactly are we going to be pushing? We're going to be pushing onto the new stack what we popped from the old stack. And this is the short way to write it. You can also write it like this right here. So it could have just been yeah, you can write it either way. But when you're calling a function, it'll take whatever is being passed in, evaluate it first, and then it'll go into the function. Because if you don't evaluate it, you don't know what it is, what the value is, if that makes sense. So it would have just popped off the element. So let's just run through what it would have done. Let's say we have a stack 1, 2, 3. Let's say this is the top right here. So 1 is the top. So we're going to pop off 1. So now we have a value 1. And this is the old one we had. And let's call this one new. So this is empty. So we're going to take this old element. Okay, now we have a 1. If you would have popped, it would have advanced forward. And now we're going to push it on. So now we have a 1. Then we're going to do the same thing here. 2, push it forward. Oh, sorry. Sorry, I meant to write it like this. So we would have popped off. Then we would have gone down to 2, then added on 3 at the end. So our top for our new stack would have been here. And the same way, if we were to pop off, so let's say we were going to do this again. We would take this element 3, go down by 1, then 2, go down by 1, and 1. And now we're back at the same state. And then if we do this again, we're going to end up, you guessed it, with 1, 2, 3, and so on. So if you just keep running this, it'll just reverse it back and forth, back and forth, back and forth. So that's kind of what's going on. So this one would have started up here, and this one would have started down here with nothing in it, and then worked this way up to its full stack. And the last thing we had to do, let's see. I don't think there's anything else to do. Let's get updated, pop. Okay, yeah, that's it. So at this point, we would have just returned the new stack that we got. And that's it. So we just popped everything off, pushed it the moment we popped it off from one second to the other, and that would have been the end of that. Let me see if anyone has a question. No. Okay, cool. So next question here. I'll have it here. Okay. So we're just on queuing onto a doubly linked list. So this is pretty similar to the DQ, but just a little different. So instead of removing something from, let's say this is your front right here. So instead of removing on this side, instead of removing from this side, we're actually going to be adding something on this side. So let's just think about that. Let me just use a different color. Let's say you want to add a new element. Let's say we want to add on, so we have 3, 4, then we want to add on a number 5. We're going to want to make a new node. So this is a new node right here, 5. But we're going to want to change what the tail was pointing to. So let's say the tail pointer, its next would have been null, since it's the tail. There's nothing else after that. So we would want to change that to be pointing to the new node. But remember, this is doubly linked. So we have a next and a previous to deal with. So for that new node, since we're going to have the tail pointing to 5 at its next, that means the previous of 5 would have to be 4. And since we're adding to the tail, we know that what used to be here was null. So we would just route the next of the new node that we're adding to be pointing to null. So we know like what the end of the list is. So on the other side, we had to deal with, for example, if we were deleting this one, if we were dequeuing, we would have had to deal with this pointer right here. And we didn't really care, since it was always at the front, what the pointers right here were pointing to. But in this case, we have 3 things to take care of. So we have this pointer, and this pointer to take care of. So let's start off. So new node star, I'm just gonna malloc it. We have our checks if it's null, if the malloc failed and everything. And data. The data is gonna be what we want to add. So it's gonna be item. The next of it, since it's always gonna be at the tail, whatever's the only thing after the tail always is gonna be null. So if this new node is gonna be the tail, and everything, and on any given linked list, the tail is going to be either null if it's empty, or if there's something in the linked list, it doesn't matter how many elements, the next of that node is going to be null. So we would just want to set this, and this is going to be our new tail, just set the next to be null. Then we have the size. So we checked if it was null, if the queue was null, if the node was null, meaning the malloc failed. And if it didn't, that means that we can add it on fine. So we would, this queue equals this queue plus size plus 1. Then if the head is null. So pretty much this is just saying if the list is empty. And at this point, it would, if it was empty, the queue size would have started at 0. And now it's at 1. That doesn't mean that it's not empty right now. Well, currently it's still empty, but we just updated the size before we actually, put the node there. So if it's empty, there's nothing to point backwards to, so it would just be null. So it's doubly linked to the previous. The head would be the node you're just adding, since there's nothing else. And the tail would also start at the same location. So this would have worked. You could have done this here, new node, or since this queue head points to new node, you could have done this as well. I don't know. I'd probably prefer to do this queue head, but it doesn't matter. You can do it however you want. And now we have 3 other lines. So to get past this block of code right here, only one thing can be true. The head is not null. That means we're not empty. So it's a case like this, 3, 4, or it could just be 3 or whatever else. So in the case that there is something, the head and tail are not going to be pointing to the same thing. So that means that, like in this example here, In this example here, the head is here, the tail is here. And like I said again earlier, if there's only one element, they would be the same, which is why we did that right over here. So they're not the same thing. And since we're adding to the tail, we would just want to deal with the tail pretty much here. These 3 lines. It was 3 lines? Yeah, 3 lines. So we're going to want to take the tail and set the next to be equal to new node. So we just added this element on. And we know that new node next. So we know that this node was already pointing to null. So we had something like this. Let's say we have 4, 5. Let's just say these dots are nodes. We had null, but then out here we have something we want to bring in. Let's say a 6. So this is what we have right now. So we have a node that hasn't been linked, but after this line, so pretty much just right here, we're going to have this right here. We just reassigned the next. So we're pointing to a list that looks like this. This is our list right now. But remember, each of these links are bidirectional. So we have a previous and an next. And right now, we've only messed with, right here on this line right here, we've only messed with the next of this one. But as for the previous, we have no idea. We have no idea what it's pointing to. So since we know that we're not at the case where it's empty, we know that the previous is not going to be null. So the previous would just be the old tail itself. So if we're adding on 6 right here, so let's say this is the tail. And we haven't changed the tail. We've only assigned the next of the tail. We're going to want to make, sorry, here we go. We're going to want to make the previous of the new tail node 6 to be pointing to the old tail. So we're going to want to do something like this. This Q tail next previous equals, and we would just set it equal to this Q tail. So this is kind of ugly. So right now we have the tail, then we're going to its next, which you just assigned to be new node, and then we're setting the previous to be equal to tail. And this works, but you know, it doesn't look nice. It's kind of weird to look at. So let's just do this. Say new node previous equals this Q tail. And then we can remove this line. That looks a lot better. So pretty much we set this to be pointing like this. So we have this right now. We have 6 pointing backwards to 5 at this line right here, 139. But then at 140, we're assigning the old tail to now point to the new node. So that's what we have right now. And now at this point, since we've linked it up properly, then we're just going to want to slide our tail down by 1. Since we just added something, this node that we just added is going to be our new tail. And that's pretty much it. So when you're dequeuing on a dequeue case, you're going to want to worry about one previous pointer, and that's pretty much it. Then when it comes to a on queue, you're going to want to worry about the previous of the new node you're adding, the next of the old tail, and then also the next of the new node that you're adding. The next of the new node is always going to be null since at the end, but you're going to have to, the important ones or the key ones that you got to think about are the tails next and the new nodes previous. That's pretty much it. Let me see if anyone has questions. Okay. All right, so that's this one. Okay, so do the thing. So this one, it's actually stacks and queues. So you're messing around with 2 stacks and 1 queue. Okay, and just some advice on these type of questions. Don't try to do it in your head, please, because I remember the first time I practiced this question, I had a couple of friends, they were trying to do it in their head, and it's just better not to, just so you don't make mistakes. Because you got 3 stacks, you're on queuing, you're popping, you're pushing, you're this, you're that. So, and there's multiple while loops, so it's better to just, you know, trace it out and see what's actually happening versus thinking you got it. So this one, I'm not going to write all this, but I guess I'll just pseudocode it. I'll write the while loop, but not the rest. So this is pretty much what it is. And also we have a print right here. And yeah, he'll actually take points off if you don't print tada. So print tada. So he's just asking what's the exact output of the function above. You may assume that all these function works. Okay. So we have a queue, we have 2 stacks. So remember, stacks are last in, first out. Queues are first in, first out. So it's important you know that. If you don't know that, then it's gonna be fun trying to solve this question. So let's start off with this for loop right here. So we're just adding everything onto stack 1. So that part is easy enough. So let me just write it out here. And by the way, one tip for these type of questions, it's a lot easier and a lot faster since you guys just have 10 minutes for these type of questions to visualize it with less elements. So I'm not actually going to use all 9 elements because that would take forever. But I will use 2 to 3 of the items because after 1 iteration, 2 iteration, you see the general pattern, and then from there, you just have to apply that to everything else that's in the data set. So let's just say this is array. So I'll just take the first 3 elements and do it with this. Like you would want to apply it, but don't forget to actually write out 23, 12, 31, however they appear. So, okay, so we just pushed 3 elements onto our stack. And let's say this is the top, so we can visualize it. So this is top right here. So while the stack is not empty, so S1 is what the whole while loop is running on pretty much. So while there's still something in this right here, so let's just, instead of array, since we're transferring it over, the array pretty much is everything that's in the stack. So let's just call this S1. So S1 is equal to this. So this is what we have in our stack. Then while the stack is not empty, we're going to unqueue it to Q. So Q is equal to 3, 18, 58. And instead of T, I'm going to use front for this one. So since we popped everything off, we now have nothing in this right here. I'm just going to keep this like this just in case. So now we're going to dequeue everything from stack 1, throw it onto stack, or from the queue, and push it onto stack 2. So stack 2, it has nothing in it. So it's the same way as S1 right now. And we're just going to push it on. So I'm going to have 3. I'm going to have 18. I'm going to have 58. So we took it out from one stack, pushed it onto the queue. Sorry, would have been 58, 18, 3. And now from here, okay, I kind of messed up that whole example. Sorry. Let me just redo it so it doesn't not make sense. So 3, 18, and 58. Normally I draw this stuff out, but okay, there we go. So this is the order we added: 3, 18, 58. Pop everything off, add it onto the queue. So we're gonna go 58. Let's do this step by step so I don't mess up. We're gonna go 18. We're gonna go 3. This still stays as our front. And then now we're gonna pop our dequeue from the queue and then add it onto the stack. So we're gonna dequeue 58. This was our top, and we're gonna move our front forward. We're gonna add something in here. That's gonna be 18. Move our top forward. It's gonna be 3. So now the top of the stack is 3. So right now we're gonna be at the print statement, and we're gonna pop off from S2. So S2, the top is 3. So this is our print sequence. We have 3. So we just removed it from here. And now while stack 2 is not empty, we're gonna push everything onto stack 1. So let's just remove everything from here. So we're gonna pop off 18, move the pointer down, and we're gonna have 58. This one would have gone up, this one would have gone down. And now stack 2 is completely empty, and stack 1 only has 2 elements. So let's just reset everything at this point. So everything would be empty. So now stack 1 is not empty. So we're gonna get the next iteration of this bigger while loop. And now we're gonna start and do the same thing again. So we'll do it one more time, and then from there, you'll see the trend and just apply it to the whole thing. So while stack 1 is not empty, I'm gonna unqueue it onto the queue. So we would have 58. Bring the pointer down. Then we have 18. And now we're empty. Now we would take everything from the queue, put it onto stack 2. So pop 58, moves the pointer up. And then now we're gonna remove 18, move the pointer up. And at this point, we're done. So queue is empty. And this is stack 2 right now. So now we're gonna pop off from stack 2. So we're gonna have 18. And I think you guys see what's going on. So it pretty much prints it in the same order that it was in the array. So yeah, that's pretty much it. That's all it does. So it takes something from one array, from one stack. So let's say 3 and 18. It'll transfer it over to a queue. So it'll flip it into 18.3. Then it'll push it onto a stack. So it'll do 3, 18. And then it'll pop it off. And then it just does that continuously. And that's how that'll work. And you also have to remember you're going to do ta-da. So that's pretty much it for this question. You would just apply it to the rest of the sequence. Let me see if anyone else has a question. Isn't it just reversing it twice? Yeah, exactly. So it reverses it. It reverses it once. So like I said, 318. Then you're going to have 18.3. From 18.3, it's going to go to 318. And then from there, pop and so on. Let's go on to, I don't know if there's another. Oh, I have, yeah, one last question. So did that get your question or no? All right. All right, so this is actually the foundation that I took. So I remember doing this one. So you guys can, I'm sure you guys have probably seen it or tried it out, but just read it. I'll write down everything we need. All right, so pretty much they want you to balance this string out or make sure if it is balanced. So let's say we have, they have the cases there, but we had something like this, then we're balanced. And I guess a way that you can think about it is when you write code. So let's see. Any example that I have, let's just use the same example. Notice how for every opening parenthesis or open squiggly, there's a second one. For every closing, there's a corresponding first. But if I were to try and compile something like this, where there's not an even, like an even number on the other side, like one that catches that opening with a closing, then my code wouldn't run. So I guess you could think of it like that. So whenever you write code, like in C, you need the squiggly brackets, and that'll, I guess, tell the compiler if it's balanced or not. And it'll say, oh, this is the end of the function, and so on. So you can think of it like that. So we're checking for two different types. So we have the squiggly, and then we have the open parenthesis, open and close parentheses. And we're trying to see if both of them are balanced. So cases like this, cases like this, these are all balanced because, let's say, for example, right here, this whole inner expression has a corresponding outer, opening, and closing. This one right here, this expression right here, this one right here, it corresponds to itself. Then it has its outer brackets as well. And this one has its own corresponding opening and closing. But let's say we had something like this right here. There's no corresponding opening that matches this one right here. So therefore, we're unbalanced. Or if we had something like this right here, this is unbalanced. Because let's say we wanted to close out everything, like going inside out. So something like, say we want to go inside out. So this one right here, we can remove it. Then let's say this one right here, we can remove it. Oh gosh, I think I accidentally deleted an extra one. There we go. Okay. Let's say we start right here. We can delete this one. Then we can delete this one right here. Keeps on deleting an extra one, but yeah, then we go like this. Then from here, we come down to this, then this, then this, then this, and then finally that. So it balances out. But on this case, you have one here and then one here, but these two can't close out. So you're overall unbalanced, even though as a whole, it closes out on the outer, but on the inner, it doesn't. So that's just the case right there. So if you think about it, at any given point, you're going to want to see if what was previously in the stack matches the type of bracket that you have. So let's say you first see an expression like this right here. So we're going to see the first opening. So we'll just push it on. And we're going to see another opening. We'll push it on. But then we're going to come to this point right here, the closing squiggly, the closing brace. And then we're going to want to see, assuming this is our stack right here, let's call this stack. Oh God, that's kind of confusing. Let's say this is the stack. We're going to want to see whatever's at the top of our stack. So whatever will be at the top right here is this opening squiggly bracket. If it matches the type of bracket that we're looking at right now. So we see this closing one right here. It's closing of the same type. So that means that we're good to go. We could pop this one off and be done with it. But let's say we had something like this right here. Then when we get to this one right here, we're going to see, oh, does what's at X match with what I have at the top of my stack? This does not match with this, so this is not valid. Therefore, at that point, we could just stop right there because, it's already invalid. Like there's no way to solve that. It's unbalanced. So that's pretty much what you're doing in code. You're just trying to see if what was at the top of my stack, if it matches what I'm putting in, if it's a closing bracket. So that's pretty much what we're going to do for both cases. We're going to check that for the squiggly bracket and then for the parentheses as well. So if we want to do a couple checks, so if we have nothing in our stack, so if is empty, and you gotta do ampersand since it's just static initialized. They always get you with that stuff, so definitely remember ampersand s instead of just s. I'll give you points off if you don't. So if it's empty, we're just gonna push on whatever's there. You could do a check to see if it's a closing or not, because if you have an expression that starts off, oh, my pad just, oh, I think it stopped sharing. Okay, sorry about that. I accidentally closed my iPad. So if you ever start off with an expression like this, has nothing in it, or it starts out with a closing bracket, then by default it's done. Like there's no way to balance it. But we're just gonna make this simple. You don't have to check for that based on what you're gonna return at the end. Like it'll end up making sense. So let's do push. And then we just want to push whatever we have onto the stack. Else, so this is the case where it's not empty. So if it's not empty, this is where we're going to want to see, based on what's coming in, meaning the element that we're currently looking at in the string, we're going to want to compare that to what's at the top, which is why they give us the peek function. So two cases is ending brace and ending parentheses. So if peek of ampersand s equals, let's say on the other side we have an opening parentheses and we have a matching of the same type. So if e of I, meaning the current element we're on, equals the opposite of that one, then we're going to want to do some stuff. But let's just write out some of the other cases. Else if peek of ampersand s equals squiggly open. So we have the two cases right here. If it's a parentheses case, that's valid, or if it's not, then like I said in that one example, like this one right here, we're going to see the first closing right here, and it matches what was at the top of the stack, which would have been what's at y right now. So we could just pop this off the stack. So if our stack looked like this, we could just pop this one off, and this would be what's on our stack right now. And again, if we go to the next element, then we're going to check the top of the stack. It matches what was previously there, so now we can pop this, and we're done. So we're just going to follow the same thing right here. So we know that the current case that we have is valid, so just do pop ampersand s and pop ampersand s. So otherwise, if it's not the case where we have something like one of these two, so we had at one point we had something like this was at the top of the stack, and then we had a corresponding close, or if we have something like this, then these are the two cases where we're good. Otherwise, if it's not one of these two cases, then it's can only be something else. So it can only be invalid. So it could only be the case where we have something like this, or if it's not that, then it would be something like this. So these are the two cases. If it's not these valid cases, it'll only be something like this, and we know that that's not valid. But if we pay attention to what is returned, it says if the expression is valid, return 1, otherwise return 0. So the thing is, we don't have enough information to just return right here. There could be some checks you can do, but we don't have enough information to just outright say, oh, we can close it off right now. So we're just gonna end up pushing onto the stack. So we're just gonna run through the whole expression that they give us, the whole string. And after we're done with it, then we're gonna wanna check one thing. Notice how in the case where it was balanced, like this one right here, we popped off, we had this in our stack, then we popped off this element, and then from there we found a corresponding closing parentheses, and then we had nothing in the stack. So this is our stack, it ended up being nothing. So ultimately, we're gonna wanna check whether or not the stack is empty. Meaning if it's empty, then you balance the stack properly and the expression is balanced. So you're gonna return is empty ampersand s equals 1, meaning that the stack ends up being empty. So the expression was properly balanced. So does anyone have any questions about that? Like this one was more complicated than all the other questions that we've done. So yeah, if anyone has any questions, let me know. Okay, so yeah, that's pretty much it for this question. This is definitely like one of the harder questions that they give, but I don't know. I feel like they definitely changed the format of the foundation with this exam. This is the one that I took. So based on all the previous ones, this one seemed a little harder, I'd say, than most of the other ones. Like the material that they give you to practice and everything. But if you know the principles pretty well, then you should be able to solve it. But yeah, it generally makes sense though. So let me just ask you guys some questions. So what do you guys want to cover next time? I can do binary tree, tries. I can go over all that stuff. So if there's anything specific or if anyone needs me to explain something again, let me know. One suggestion. Okay, definitely. Yeah, yeah. I'll definitely go back and do that. Is there any one specifically like you want me to explain more? Now that I think about it, yeah, I probably should have done that. Yeah, that makes sense. Thing is, I was writing all the code while you guys were reading, so I just skimmed over it and then I looked at it and just thought of the answer. But yeah, I'll definitely go over it. I can see why that's important because how you read it is also important to how you solve it. And yeah, that bitwise question was rough. I remember reading it. It was the painting fence question. But let me just say something about that. A lot of those questions, especially when they give you the story, like on the last one, there was some frog in a well. There's also, painting a fence and all these sort of things. They give you a big, big story. Most of it is literally useless, but there's usually one or two sentences that are really important. If you go back to that question, the second paragraph, last sentence, so they throw it deep in the middle of the story that they give you. There's a section or a sentence that says, "Notice how the fence stays painted if it was already painted." So, like, if you've already painted over a section, it stays painted. So that would have given away the type of operator you use, which was or. But yeah, that's just about that question real quick. So yeah, you have to sift through all the storytelling sometimes. But I'll definitely go over that and do that for the next time. And I'll cover recurrence, relation, summation. I'll cover it probably the week before. Probably the week before, because there's still a lot of stuff that's left to cover. So if I would have started this stuff earlier, it would have been better. But I've only been 2 weeks, and I kind of spent too much time on DMA and linked lists than I had expected. It was my first time, so I didn't really know how to time myself and everything. But this time was better, and yeah, I'll definitely do that. Probably the week before the foundation or the week of. So the exam is the 21st. So I'll do that. I think it's the 18th, the Wednesday. But next week, I want to knock out binary tree, try, and I guess also heap. Maybe even a little hash table, because hash table doesn't take too long. It's pretty easy. When it gets to heap, it's pretty much they just ask you questions where you're removing or you're adding something onto a heap and you gotta, rebalance everything and all that stuff. Or it might be a question like critical thinking type of question, which I've seen maybe 2 or 3 times, but normally they just ask you if you're adding stuff on. Also, oh yeah, sorting as well. Yeah, I can do sorting questions. But yeah, so it would be the last week on the week of the exam. I'll do recurrence and summations, and yeah, I can do try, recursion, or what specifically would you want to see on try though? Because to be honest, there's not that many questions on tries that come up. They definitely do show up, but it's very like some here and there. It's not too common. I know the last one they had one where it was like you're counting how many nodes you would have to make if you add on a string. But is there anything specific on them that you don't get? Okay. All right then. So yeah, I'll see you guys. Oh wait, you give insights and strategy on how to solve them. So I think I would just like to see it in general. Okay, okay, cool. Yeah, definitely. Yeah, I'll go into that next week. Honestly, next week I'm probably gonna do a longer one since there's like so much left. I'm probably gonna run it longer. So if you guys could stay around a little longer. It'll be on YouTube either way, if you can't make it or you can't stay the whole time. But I'll probably run through a lot of topics. Sorting won't take too long. When it comes to heaps, won't take too long. Hash table won't take too long. Binary tree and tries, that'll take a little longer because those are topics that people generally, have some trouble with. Because it's heavy with recursion, stuff like that. But yeah, I'll do all that stuff next week. I'll probably go maybe like 5 to 7:45 or something like that instead of 6:45. But yeah, I'm gonna cut it off here. So I'll see you guys next week.